We're continuing with section 3.4 and physics, gravity. And so Newton's law of gravitation say that the magnitude F of the force exerted by a body of mass m on a body of mass m, lowercase capital case, the capital letter, is F equal to G times m, lowercase m, times upper capital M, where G is the gravitational constant, 6.6741 times 10 to the power negative 11 cubic meters per kilogram times square seconds, and R is the distance between the bodies. And so if we want to calculate the derivative of F with respect to R, or the distance between them, treating the masses as constants, what we get is basically, so we're also not only considering G as constant, we're considering M and M as the lowercase and capital M as constant. In that case, and it would be the constant times derivative of R to the power negative 2. And that would be negative 2R to the power negative 3. So it's negative 2GMM divided by R to the power 3. But comparing this to what we started with, this one with what we started with, the difference is on, and it's actually, this one is negative 2 times that divided by R. And what is the physical interpretation of this? Means that as distance increases, the gravitational force is decreasing at lower and lower rate. So the gravitational force weakens at a slower rate as the distance between bodies increases. So let's talk about biology and population growth. Let n be f of t be the number of individuals in an animal or plant population at time t. The average rate of population growth during the interval t1 to t2 is delta n over delta t, which is basically change in f, which is f of t2 minus f of t1 over change in t, t2 minus t1. This population in so we are going to talk about the instantaneous rate of growth that is obtained by basically setting delta t going to 0, limit of this as delta t goes to 0. But you have to be careful. The population growth is not continuous. It's really a step function. Here, step function, it's just number over time increases by 1, and for a while, or I say there are 8 of them in there, and then they have children after a while, and they become 30, and then those 30 have children after a time, and it gets more and more. And so it's not really a continuous function. But because these step functions are going to be a little closer to each other, let's say in when bacteria is growing, or so on and so forth, then you can basically with a longer period of time, they look like a continuous function, and we can use a modeling to approximate a continuous function modeling to approximate their rate of change, instantaneous rate of change, and a little bit of a calculus of plumbing. The water temperature T in a shower and in degrees Celsius is controlled by a knob. Let A be the angle of the knob in standard position as shown. What can you say about dTdA? Okay, so my first question is if this knob is working correctly for every basically the dTdA should be a constant function and going from every for every increase equal increase in A, you should get an equal increase in T. And so basically it should be an increasing function and it should match the degrees over here. So every let's say over here I have pi 6th increase, so I have to have basically 30 per pi 6, 10 degrees Celsius per pi 6 increase. Now, what if the plumber is having problem when if the dTdA is too small? dTdA is too small is that we're increasing, it's supposed to, for example, go to 70 degrees and it's not doing that. So what could be a cause of a problem? It could be that there is not enough hot water supply. What if the dTdA is too large? Then there is too much, like water is too hot, the water heater is heating it up too much. So turn down the water heater. What if the dTdA is equal to 0? Either the knob isn't working or the heater is not working at all. What if the dTdA is less than 0? Knob is installed backward